Spring arrived late in northern Germany during 1943. At a Luftwaffe airfield north of Berlin, a peculiar scene unfolded that would shake German aviation confidence to its core. Inside a maintenance hangar, German engineers gathered around what appeared to be an impossibility. A British bomber, constructed almost entirely from wood, that had been outrunning Germany's finest metal fighters for over a year. The aircraft sitting before them was a de Havilland Mosquito, forced down 3 days earlier due to mechanical failure rather than German action. For months, Luftwaffe pilots had filed frustrated reports about this mysterious British plane. It photographed Berlin in broad daylight. It struck targets with surgical precision. Most infuriatingly, it simply accelerated away whenever German fighters attempted interception. Now finally, the Luftwaffe had an intact example to examine. The officer assigned to lead the technical assessment was a veteran fighter commander who had flown combat missions since the war's opening days. He had engaged Polish fighters in 1939, tangled with French aircraft in 1940, and dueled Spitfires over the Channel. He understood aircraft design, aerodynamics, and combat performance. Everything in his experience said this wooden British machine shouldn't be possible. Germany had invested enormous resources developing advanced aviation technology. The Messerschmitt and Focke-Wulf fighters represented cutting-edge engineering, built from aluminum alloys using precision manufacturing techniques. Germany's jet-powered fighters were beginning test flights, promising speeds no propeller aircraft could match. German aviation was supposed to be the world's most advanced. Yet this wooden relic had made fools of the Luftwaffe for 18 months. Reports documented mosquitoes photographing sensitive targets from altitudes German fighters couldn't reach. They described precision bombing attacks on Gestapo headquarters in occupied Norway. They detailed nuisance raids on Berlin, timed to disrupt speeches by senior Nazi officials. The psychological impact was devastating. How could German citizens believe in their air force's superiority when British wooden bombers struck the capital with impunity? Walking slowly around the captured aircraft, the German commander tried to reconcile what he knew with what he saw. The fuselage was beautifully shaped with aerodynamic lines suggesting speed. The wings appeared thin and delicate. The engines were Rolls-Royce Merlins, the same reliable power plants used in Spitfires. Nothing exotic. Nothing Germany couldn't theoretically match or exceed. But it was built from wood. He knocked on the fuselage, hearing a hollow sound like tapping a shipping crate. Throughout his career, he had flown metal fighters. Metal meant strength, durability, modernity. Wood meant obsolescence, relics from the previous war's era of fabric-covered biplanes. The cognitive dissonance was overwhelming. How could this wooden machine outperform Germany's finest metal fighters? The examination would soon provide answers that challenged fundamental assumptions about modern warfare and industrial competition. To understand why those answers proved so troubling, we must return to the Mosquito's unlikely origins in pre-war Britain. In 1938, as Europe moved inexorably toward war, the British Air Ministry focused on two aircraft types: heavy bombers and interceptor fighters. The prevailing doctrine for bombers emphasized defensive armament. Bombers would bristle with gun turrets, carry armor plating to protect crews, and rely on formations for mutual defense. All this protection added weight, reducing speed and operational ceiling. Geoffrey de Havilland, founder of the de Havilland Aircraft Company, proposed something radical. What if Britain built a bomber so fast it didn't need defensive guns? What if it simply outran enemy fighters rather than fighting them? What if it was constructed primarily from wood, using Britain's abundant timber and skilled furniture craftsmen rather than competing for scarce aluminum? The Air Ministry rejected the proposal repeatedly. They wanted heavy bombers capable of carrying massive bomb loads deep into enemy territory. They wanted fighters to protect British airspace. They emphatically did not want an unarmed wooden aircraft from a designer who seemed to be ignoring modern aviation trends. De Havilland persisted with stubborn determination. He had been designing and building aircraft since 1910, 3 decades of experience spanning the aviation industry's entire history. His company had produced everything from simple trainers to racing aircraft to commercial transports. He understood wood construction intimately, knowing its strengths and limitations far better than critics who dismissed it as obsolete. More importantly, de Havilland recognized that Britain's strategic situation demanded creative solutions. Aluminum production was severely limited. Skilled metalworkers were in short supply, needed for producing fighters and other essential aircraft. But Britain possessed vast forests and a sophisticated furniture industry, employing thousands of craftsmen with precision woodworking skills. A wooden aircraft could be built in facilities that couldn't produce metal planes, using workers who couldn't be diverted to other aviation projects. In November 1938, de Havilland submitted a formal proposal outlining specifications that seemed wildly optimistic. A bomber capable of 400 miles per hour at 15,000 feet altitude, powered by 2 Merlin engines, range of 1/500 miles, carrying a 1,000-pound bomb load, requiring no defensive armament because it would be too fast to intercept. The Air Ministry called it unrealistic and rejected it. De Havilland continued advocating throughout 1939 while war clouds gathered. Germany invaded Poland in September. Britain declared war. The Luftwaffe began bombing British cities. The RAF desperately needed aircraft, any aircraft that could contribute to the war effort. Finally, in December 1939, the Air Ministry reluctantly authorized construction of a single prototype. They didn't believe in the concept, but they were willing to let de Havilland prove himself wrong at his own company's expense. The project would proceed without government funding or official enthusiasm. The prototype took shape at a requisitioned country house in Hertfordshire, away from the main factory. Chief designer Ronald Bishop led a small team tackling an enormous challenge. Create an aircraft matching fighter performance while carrying bombs, using construction materials most aviation engineers considered obsolete. Their solution was laminated wood construction of extraordinary sophistication. The fuselage would be built in 2 halves, each shaped from multiple wood layers bonded with advanced adhesive. Birch plywood formed inner and outer surfaces. Ecuadorian balsa wood provided a lightweight core between them. The entire sandwich was shaped in massive concrete molds under heat and pressure, creating smooth, strong aerodynamic shells that were then joined along the center line. This created a fuselage that was effectively a single molded composite structure rather than a metal framework covered with panels. The outer skin wasn't just covering, it was the structure itself, contributing directly to overall strength. The wings used similar principles with different details. Spruce wood spars provided main structural members. Plywood ribs created the airfoil shape. Plywood skin covered everything, creating what engineers call a stressed skin structure, where the covering contributes to strength. The result was remarkably strong for its weight, actually stronger in some respects than equivalent metal structures, because wood's natural grain could be oriented for maximum strength in critical directions. The adhesive was crucial to everything. De Havilland used a synthetic resin called aerolite, developed specifically for aircraft construction. This glue was stronger than the wood itself when properly cured. Joints would fail in the wood before failing at the glue line. The adhesive also resisted moisture, fungi, and temperature extremes, critical for an aircraft operating from Scottish bases to North African deserts, from sea level to 30,000 feet. Construction took place in furniture factories across Britain. Companies that had built dining tables and bedroom sets before the war now shaped aircraft components. The craftsmen brought precision woodworking skills honed over decades. They could create complex curves, execute perfect joints, and finish surfaces to tolerances measured in thousandths of an inch. Skills that seemed irrelevant to modern warfare suddenly became strategically vital. The prototype first flew on November 25, 1940. Geoffrey de Havilland's son, also named Geoffrey and serving as test pilot, lifted the aircraft from Hatfield Aerodrome and immediately discovered something remarkable. The plane was extraordinarily fast. Even with prototype engines producing less power than planned production versions, it reached nearly 400 miles per hour in level flight. It handled beautifully, both responsive and stable. It climbed rapidly. Most importantly, it did everything the designer had promised and the Air Ministry had doubted. Performance testing continued through early 1941, revealing capabilities that exceeded even optimistic predictions. The Mosquito proved faster than Spitfires at altitude. It could cruise at speeds German bombers only achieved in emergency dives. Range exceeded specifications. Handling remained benign, meaning average pilots could fly it without exceptional skill. The wooden construction showed no structural weakness whatsoever. Actually, wood proved more tolerant of combat damage than metal in certain respects. Bullet holes didn't propagate into structural tears the way cracks could spread through aluminum. Small arms fire that would crack and weaken metal simply punched clean holes through wood that didn't compromise overall structural integrity. The Air Ministry's skepticism evaporated as test data accumulated. Orders flooded in for multiple variants. The Mosquito would serve as a bomber, reconnaissance platform, night fighter, pathfinder, and strike aircraft. Eventually, more than 30 variants would serve in roles from submarine hunting to precision attacks on specific buildings. Production ramped up through 1941 and 1942, spreading across multiple factories and eventually reaching Canada and Australia. By early 1943, over 1,500 Mosquitoes had been built. They were appearing over Germany with increasing frequency, flying missions that seemed impossible to Luftwaffe commanders. They photographed targets from altitudes and speeds that made interception nearly hopeless. They bombed with precision heavy bombers couldn't match. They demonstrated that unconventional thinking and creative use of available resources could produce results conventional approaches couldn't achieve. The Luftwaffe desperately needed to understand this wooden anomaly. When they finally obtained an intact example in May 1943, the examination would provide answers. Some were technical, others were psychological. All were uncomfortable for an air force that believed it represented aviation technology's pinnacle. The disassembly began with methodical German precision. Technical specialists who had examined captured British and American aircraft for years approached the Mosquito systematically. Every component would be measured, weighed, tested, and documented. Nothing would be assumed. Everything would be verified. The first surprise came when technicians removed inspection panels. Where they expected metal framework, the stringers, longerons, and formers defining conventional aircraft structure, they found shaped wood throughout. The fuselage wasn't a metal framework covered with wooden panels. It was engineered wood, laminated, and formed into a structure requiring no internal skeleton. The chief engineer ran his hand along interior surfaces. The plywood was smooth and precisely fitted, with joints so tight they were barely visible. He knocked on various sections, listening carefully. The sound was solid and dense. The wood had been impregnated with resin, making it resistant to moisture and dramatically stronger than raw timber. He had expected crude construction, perhaps adequate for a wartime stopgap, but inferior to metal. What he found was sophisticated engineering that challenged his assumptions about modern aircraft design. The wing attachment points drew particular attention. In metal aircraft, wings bolted to reinforced fuselage sections through heavy metal fittings, distributing loads into structural framework. The Mosquito's wings attached through wooden joints, reinforced with metal plates, but the primary load path went directly into the laminated wood fuselage structure. Wood itself was carrying flight loads that typically required metal. Engineers ordered comprehensive stress analysis and materials testing. They needed to understand these strength characteristics that defied conventional wisdom. The Merlin engines were familiar territory. Rolls-Royce Merlin 21s, each producing 1,260 horsepower at 3,000 revolutions per minute. These were essentially identical to engines powering Spitfire Mark I's, which German pilots respected as formidable opponents. The Mosquito had two of them, providing combined power of approximately 2,500 horsepower. For an aircraft this size, wingspan 54 feet 2 inches, length 40 feet 6 inches. The power-to-weight ratio was exceptional. Technicians weighed components as they removed them. The fuselage structure came in far lighter than an equivalent metal airframe would weigh. Wood's strength-to-weight ratio, when properly engineered, matched or exceeded aluminum in many applications. But wood offered another crucial advantage. It didn't require the massive stamping presses, extrusion equipment, and specialized tooling that metal construction demanded. The British were building high-performance aircraft using techniques furniture makers understood. This had profound strategic implications that German analysts were beginning to recognize. The absence of defensive armament became more understandable as examination proceeded. Every gun turret added weight, drag, and complexity. A typical British bomber carried multiple turrets, gunners, ammunition, and structural reinforcement to handle recoil loads. All that weight reduced speed and operational ceiling. The Mosquito carried none of it. The saved weight went into fuel, bombs, and additional speed. The entire design philosophy was fundamentally different. Avoid the enemy rather than fight the enemy. Survive through speed rather than firepower. Fuel capacity revealed another aspect of the design's sophistication. The Mosquito carried 545 imperial gallons in wing tanks and fuselage cells. At economical cruise settings, this gave range exceeding 1,500 miles. The British could strike targets deep in Germany, photograph them, and return to England without the massive fuel loads heavy bombers required. A Lancaster bomber carried 2,400 gallons, but needed it to haul 7 tons of bombs with a 7-man crew. The Mosquito carried 1,400 pounds of bombs with a 2-man crew and achieved similar or better range with less than 1/4 the fuel. The efficiency was remarkable. The bomb bay was compact but cleverly designed. 4 500-pound bombs could be carried internally, or a single 4,000-pound blockbuster, bombs loaded vertically through belly doors, nested closely together. No complex racks, no heavy structural supports for external stores. Everything internal, minimizing drag. The bomb aimer's position in the nose gave excellent visibility for precision attacks, something heavy bombers struggled to achieve from high altitude. This explained the surgical strikes on specific buildings that had embarrassed German commanders. As examination continued through May, a picture emerged that troubled the assessment team. The Mosquito represented a fundamentally different approach to bomber design, achieving strategic effects through speed and altitude rather than defensive firepower and armor. More concerning, it achieved this performance using materials and construction methods Britain could sustain indefinitely. Germany's bomber production was constrained by aluminum shortages and competing demands from fighter production. Britain had apparently circumvented that constraint entirely. The captured Mosquito couldn't fly. The pilot had sabotaged engines before capture, but the Luftwaffe had other ways to verify performance claims. Intelligence reports, combat encounter data, and mathematical analysis could reconstruct the aircraft's capabilities. The assessment team assembled every available piece of information about Mosquito operations over the previous 18 months. The reconnaissance variants like the captured aircraft had been particularly troublesome. These aircraft flew photographic missions over German-occupied territory and the Reich itself, flying so high and fast that interception was nearly impossible. The first recorded mission occurred in September 1941, when a Mosquito photographed targets in France. The aircraft flew at approximately 30,000 feet, higher than most German fighters could effectively operate, at speeds exceeding 350 miles per hour at that altitude. Fighter command records showed dozens of attempted interceptions following a consistent pattern. Radar would detect an inbound target. Fighters would scramble, climbing hard to altitude. By the time they reached operational height, the Mosquito had already photographed its target and was accelerating away. The Messerschmitt Bf-109G could reach perhaps 370 miles per hour at 30,000 feet under ideal conditions, but it took time to accelerate, and the Mosquito already had a speed advantage. Pursuing fighters found themselves chasing a target that was pulling away. On December 6, 1942, Mosquitoes photographed Berlin in broad daylight. The audacity was remarkable, flying over the Reich capital, photographing government buildings and industrial facilities, then escaping before effective response could be organized. Hermann Göring was reportedly furious. The mission proved Britain could strike anywhere in Germany with relative impunity, at least with fast reconnaissance aircraft. What was photographed today might be bombed tomorrow. The bomber variants were equally problematic. Mosquito bombers conducted nuisance raids on Berlin throughout spring 1943, timed to disrupt sleep and force civilians into shelters. The psychological impact was significant. German civilians who had been told the Luftwaffe controlled the skies heard air raid sirens nightly as fast British bombers struck and escaped. The raids didn't cause massive damage. A handful of aircraft carrying a ton or so of bombs each couldn't match the destruction of a heavy bomber stream, but they demonstrated vulnerability and kept the population anxious. More concerning were precision strikes. On January 30th, 1943, Mosquitoes attacked Berlin during a scheduled daylight speech by Göring, forcing him to postpone the broadcast. On September 30th, 1942, Mosquitoes struck Gestapo headquarters in Oslo, Norway with remarkable precision, destroying German records while minimizing Norwegian civilian casualties. These weren't terror attacks or area bombing. These were surgical strikes using speed and accuracy instead of mass. This capability troubled German military planners deeply. The assessment team reviewed combat reports from experienced fighter pilots. One Oberleutnant flying a Bf-109G had encountered a Mosquito on February 14, 1943. He climbed to engage, reaching 28,000 feet where his aircraft was near its performance limit. The Mosquito was already at 32,000 feet. The German pilot pushed his engine to emergency power, closing the altitude gap slightly. The Mosquito simply accelerated. His combat report was blunt. Target maintained speed advantage throughout engagement, unable to close to firing range, broke off pursuit due to fuel state. Another pilot, a highly experienced fighter leader commanding an elite unit stationed in France, wrote an assessment in March 1943. His fighters regularly encountered mosquitoes crossing the channel. His evaluation was damning. The British Mosquito bomber and reconnaissance aircraft represents a serious threat that current fighter tactics cannot effectively counter. The aircraft's speed at altitude exceeds our intercept capability. Recommendation: develop dedicated high-altitude interceptor, or accept that mosquitoes will operate with relative impunity. The Focke-Wulf 190, Germany's other frontline fighter, fared no better. The FW-190A had excellent performance at low and medium altitudes, but above 25,000 feet, it lost effectiveness. The engine's supercharger couldn't maintain power in thin air. Mosquitoes typically operated above that altitude when flying reconnaissance, missions or penetrating defended airspace. German fighters below them could see the contrails but couldn't reach the aircraft making them. Some pilots reported success against mosquitoes at lower altitudes, particularly when British aircraft were operating in ground attack or night fighter roles, where they weren't trying to run but were maneuvering to engage German targets. But reconnaissance and bomber variants flew high and fast, and interception success was rare. Intelligence estimates suggested fewer than 5% of mosquito sorties over German-occupied territory resulted in successful interception. The British were losing mosquitoes primarily to accidents, weather, and mechanical failures, not to German fighters. The implications were deeply uncomfortable. Germany had invested enormous resources developing advanced fighter aircraft. The Bf-109 had evolved through multiple variants, each incorporating combat lessons, each pushing performance higher. The FW-190 had been designed as a modern fighter using the latest engineering knowledge. Germany had pioneered jet aircraft development with the Me-262 beginning flight testing. German aviation engineering was supposed to be the world's finest, yet Britain had built a wooden aircraft that German fighters couldn't catch. The psychological impact went beyond mere performance comparisons. The Mosquito challenged fundamental assumptions about modern warfare and industrial competition. German military doctrine emphasized advanced technology and precision engineering. Reich propaganda constantly reinforced themes of German technical superiority. German workers were told they built the world's finest weapons. German soldiers were told they fought with better equipment than their enemies. The Mosquito suggested that clever design and efficient use of available resources might matter more than technological sophistication. Britain wasn't trying to out-engineer Germany. Britain was using wood, material available in every forest, to create aircraft Germany's advanced metal fighters couldn't intercept. The strategic implications were profound. If wooden aircraft could achieve such performance, what other assumptions about modern warfare might be wrong? The assessment commander drafted his report in late May 1943. The document was technical, detailed, and as objective as possible given uncomfortable conclusions. The Mosquito's performance claims were accurate. The aircraft could indeed exceed 400 miles per hour at altitude. It could operate above 30,000 feet. Its range allowed deep penetration into German airspace. Most critically, current Luftwaffe fighters could not reliably intercept it. The report included recommendations. Germany needed high-altitude interceptors capable of sustained performance above 30,000 feet. Improved superchargers or turbochargers were essential. Alternatively, jet fighters like the Me-262 might provide sufficient speed advantage if the jet program could be accelerated and made reliable. Ground-based solutions were also suggested. Improved radar, better coordination between detection and interception, positioning fighters at altitude before mosquitoes arrived. But implementing this effectively across all of occupied Europe would be extremely difficult. The report went up the chain of command. Senior officers read it with varying reactions. Some acknowledged the problem and supported developing countermeasures. Others resisted conclusions, implying German technical inferiority. The political atmosphere in the Third Reich made it dangerous to suggest the enemy might have advantages, even when evidence was overwhelming. Göring, in particular, was known to react badly to reports suggesting Luftwaffe inadequacy, but reality couldn't be denied indefinitely. Mosquitoes continued operating over Germany throughout 1943 and into 1944. They photographed targets, bombed Berlin, and demonstrated that fast, unarmed aircraft could survive in defended airspace through speed alone. German aviation designers began work on advanced interceptors, but development took time and resources were increasingly constrained as the war situation deteriorated. For German pilots, the Mosquito became a symbol of frustration. They could see them, track them on radar, attempt interception, and watch helplessly as British aircraft accelerated away. The psychological impact was corrosive. If Germany's fighters couldn't catch a wooden British bomber, what did that say about German technical superiority? What did it say about the war's likely outcome? The examination had provided answers to technical questions. It had verified performance. It had explained construction methods, but it had also forced a reckoning with uncomfortable truths. Sometimes unconventional approaches worked better than conventional wisdom predicted. Sometimes resource constraints drove innovation that technological advantages couldn't match. Sometimes the enemy was more clever than you wanted to. Admit the Mosquito's dominance only intensified as 1943 progressed into 1944, later variants incorporated. Improvements making an already difficult interception problem nearly impossible. The B Mark 16th bomber variant, entering service in late 1943, featured pressurized cabins allowing crews to operate comfortably at extreme altitudes. The FB Mark 6 fighter bomber variant added 4 20mm cannons and 8 rockets, transforming the Mosquito into a devastating ground attack platform while maintaining its speed advantage. Production numbers told their own story. By the end of 1943, de Havilland and associated manufacturers were producing over 200 Mosquitoes monthly. British factories that had made furniture were now building combat aircraft at a rate that strained German intelligence analysts' credibility. The answer lay in resource allocation Germany couldn't match. While the Reich struggled with aluminum shortages and competing demands from fighter and bomber programs, Britain's Mosquito production used entirely separate supply chains. Timber came from Canadian forests, shipped across the Atlantic despite U-boat threats. Balsa wood core material came from Ecuador, transported through supply routes. German submarines couldn't effectively interdict. British furniture factories employed craftsmen whose skills were irrelevant to metal aircraft production, but perfectly suited to Mosquito construction. Women who couldn't perform heavy metalwork excelled at the precise woodworking Mosquito construction required. The whole production system existed parallel to conventional aircraft manufacturing, adding capacity rather than competing for it. Mosquito operations expanded into roles the aircraft's designers hadn't originally envisioned. Night fighter variants equipped with airborne radar proved devastating against German bombers attacking British cities. The Mosquito's speed allowed it to catch bombers, and its heavy cannon armament destroyed them efficiently. German bomber crews who had terrorized British civilians during the Blitz now found themselves hunted by an aircraft they couldn't escape. Pathfinder squadrons used Mosquitoes to mark targets for heavy bomber streams. Fast Mosquitoes would arrive first, identify targets visually or by radar, drop colored markers, then escape before the main bomber force arrived. The technique dramatically improved bombing accuracy. German defenders had to choose between engaging the Pathfinders, fast aircraft difficult to intercept, or waiting for the main bomber stream. Either way, Mosquitoes made heavy bombers more effective. Perhaps most galling for the Luftwaffe were light bomber raids. Small formations of Mosquitoes, sometimes as few as 4 aircraft, would strike targets across occupied Europe and Germany itself. They bombed railway junctions, industrial facilities, and administrative centers with precision-heavy bombers couldn't match. The damage from individual raids was modest, but the cumulative effect was significant. More importantly, the psychological impact was profound. German air defenses built to counter massive bomber formations struggled to engage small, fast targets that could strike anywhere. On January 30th, 1944, Mosquitoes executed perhaps their most audacious mission. That morning, 18 aircraft attacked Amiens prison in occupied France. The objective was surgical precision. Breach prison walls to allow French resistance members to escape while minimizing casualties among prisoners. The Mosquitoes attacked at low altitude, bombing with remarkable accuracy. Walls were breached. Guard quarters were destroyed. Over 250 prisoners escaped, including many resistance fighters scheduled for execution. The raid demonstrated capabilities conventional bombers simply couldn't achieve. Precision, speed, and daring combined in a single operation. German fighter development struggled to respond. The Focke-Wulf Ta-152, designed partly to counter high-altitude threats, wouldn't reach operational service until late 1944. and production numbers remained small. The Messerschmitt 262 jet fighter had speed to catch mosquitoes, but mechanical reliability problems and fuel shortages limited its effectiveness. Even when Me-262s did intercept mosquitoes, the jet's limited endurance meant brief engagement windows. By mid-1944, the Luftwaffe had essentially accepted that mosquitoes would operate with relative impunity over German airspace. Fighters were increasingly reserved for engaging heavy bomber formations where interception had better success rates. The Mosquito's success forced uncomfortable questions about military procurement and industrial strategy extending far beyond one aircraft type. Germany's aviation industry had pursued technological excellence through increasingly complex, resource-intensive designs. Each new fighter variant incorporated advanced features, pressurized cockpits, sophisticated weapons systems, powerful engines requiring exotic materials. These aircraft were formidable when they worked, but they were difficult to build, maintain, and operate. Production numbers suffered because each aircraft required extensive specialized labor and materials. Britain's approach with the Mosquito was philosophically different. Rather than pursuing maximum technological sophistication, de Havilland had optimized for performance achievable with available resources. The result was an aircraft that performed better than competitors in many mission profiles while using materials and manufacturing techniques Britain could sustain indefinitely. The strategic wisdom of this approach became apparent as the war continued and Germany's resource situation deteriorated. By 1944, German industry was producing remarkable aircraft, the Ta-152, the Me-262, the He-219, but in numbers too small to affect the war's outcome. 100 advanced fighters couldn't defend the Reich when thousands of Allied aircraft filled the skies. Meanwhile, Britain was building Mosquitoes by the hundreds monthly, using resources that didn't compete with Spitfire, Lancaster, or other aircraft production. The Mosquito added capability Germany couldn't match, because Germany had no equivalent resource pool to draw from. The psychological impact on German military leadership was corrosive. The May 1943 report had warned the Mosquito represented a serious threat, requiring dedicated countermeasures. Those countermeasures never materialized in effective form. The Luftwaffe's response was essentially to accept it and focus resources elsewhere. This acceptance represented a profound shift from early war, confidence that German engineering would prevail through technical superiority. German pilots who had flown against Mosquitoes consistently described a sense of futility. They could see the enemy, could attempt interception, could even occasionally engage at disadvantageous ranges, but they couldn't prevent Mosquitoes from accomplishing their missions. The most successful German night fighter pilot with 121 confirmed victories described the Mosquito as the aircraft we most feared, despite having shot down several himself under favorable circumstances. When the enemy you most feared was made of wood and plywood, what did that say about your own technological advantages? Post-war analysis conducted by Allied intelligence teams examining captured German documents revealed the extent of Luftwaffe frustration. Internal memos showed repeated demands for solutions to the Mosquito problem. Aircraft designers responded with proposals for high-altitude interceptors and jet fighters, but proposals required time to develop, resources to build, and operational circumstances to deploy effectively. Germany had none of these in sufficient measure. By late 1944, the Reich's industrial capacity was crumbling under Allied bombing. Resources were critically short. Experienced pilots were increasingly scarce. The Mosquito flew its final combat missions in May 1945 as the war in Europe ended. The aircraft had been produced in over 30 major variants, serving in roles from high-altitude reconnaissance to anti-shipping strikes. Total production exceeded 7,800 aircraft built in Britain, Canada, and Australia. Operational losses were remarkably low for an aircraft that flew combat throughout the war. The speed and altitude performance that made interception difficult also made survival likely. German records captured after the war showed Mosquito loss rates over German-occupied territory were approximately 3% of sorties flown, compared to 5 to 8% for heavy bombers during the same period. The Mosquito's design philosophy, speed as survival, had been vindicated by operational results. The aircraft proved unconventional solutions could outperform conventional approaches when design priorities aligned properly with operational requirements and industrial capabilities. The German officer who examined the captured Mosquito survived the war. He was captured by American forces in May 1945 and spent 2 years in detention before release. In post-war interviews, he spoke candidly about the examination. He acknowledged the aircraft had challenged his assumptions about aviation engineering and modern warfare. He admitted Germany's response had been inadequate, hampered by resource constraints, competing priorities, and institutional reluctance to acknowledge the enemy might have designed something genuinely superior in certain respects. The de Havilland Mosquito remained in service with various air forces until the 1950s. The Royal Air Force retired its last operational Mosquitoes in December 1955. The aircraft had served for 14 years, a remarkable lifespan for a design critics had initially dismissed as obsolete before it flew. Several air forces continued operating Mosquitoes into the 1960s for specialized roles. The Israeli Air Force flew Mosquitoes during the 1948 Arab-Israeli War. The Dominican Republic operated them into the mid-1950s. The aircraft's basic soundness and performance longevity validated de Havilland's unconventional approach. Modern aviation historians studying the Mosquito consistently identify it as one of World War II's most successful aircraft, designs when measuring performance against production cost, operational effectiveness, and strategic impact. The aircraft cost approximately half what a Lancaster bomber cost to build, flew missions the Lancaster couldn't attempt, and survived at higher rates. It demonstrated that creative engineering using available resources could produce results brute force technological development couldn't match. The Mosquito's influence on post-war aviation design was subtle but significant. The aircraft proved multi-role capability had genuine value, a single airframe serving effectively in reconnaissance, bombing, night fighting, ground attack, and anti-shipping roles simplified logistics and training. Later multi-role aircraft like the F-4 Phantom in American service or the Tornado in European service owed conceptual debts to the Mosquito's operational flexibility. More importantly, the Mosquito validated the principle that operational requirements should drive design choices rather than technological fashion. In an era when all metal construction was considered modern and advanced, de Havilland chose wood because it better served his objectives. The decision was pragmatic rather than ideological. The result was an aircraft that performed brilliantly in its intended roles and adapted successfully to roles never initially envisioned. For Luftwaffe pilots who faced Mosquitoes, the aircraft represented a turning point in their understanding of the war. Early in the conflict, German pilots believed their equipment and training gave them decisive advantages. Encountering enemies they couldn't catch, couldn't shoot down, couldn't prevent from completing their missions eroded that confidence. The Mosquito wasn't the only factor in this psychological shift. Allied numerical superiority, improving Allied tactics, and deteriorating German circumstances all contributed. But it was a particularly visible symbol of how technological assumptions could be wrong. The captured Mosquito, examined in May 1943, remained in German hands until the war's end. It was eventually recovered by British forces and returned to the United Kingdom. Several Mosquitoes survive today in museums worldwide. The de Havilland Aircraft Museum in England preserves the prototype that first flew in November 1940. The Royal Air Force Museum displays multiple variants. The Canadian Warplane Heritage Museum operates a flying example. These preserved aircraft allow modern viewers to examine the construction techniques that confounded German engineers 8 decades ago. Standing beside a Mosquito today, you can knock on the fuselage and hear that hollow sound. You can see the wooden construction, the elegant lines, the compact bomb bay, the absence of defensive armament. The aircraft looks deceptively simple. 8 decades later, the lessons endure. Technological sophistication doesn't guarantee success. Unconventional approaches sometimes produce better results than conventional wisdom predicts. Resource constraints can drive innovation that abundance cannot. And sometimes the enemy surprises you with something that shouldn't work but does. And all you can do is acknowledge the reality and wish you had seen it coming. The Mosquito story offers insights that extend beyond aviation history into broader questions about innovation, industrial strategy, and organizational adaptation. When we examine why this wooden aircraft succeeded so dramatically, we find lessons applicable to any competitive environment where resources are limited and conventional wisdom dominates. First, the Mosquito demonstrated that constraints can be catalysts for creativity. Britain faced severe aluminum shortages and competition for skilled metalworkers. Rather than accepting reduced aircraft production, De Havilland reconceptualized what a modern combat aircraft could be. He didn't ask how to build a better metal bomber. He asked what performance was actually needed and what resources were actually available. This reframing was crucial. German designers were optimizing within conventional parameters, creating better versions of what everyone agreed aircraft should be. De Havilland was questioning the parameters themselves. Did bombers really need defensive armament if they could be fast enough? Did high-performance aircraft really require metal construction? Could furniture craftsmen contribute to aviation production? Each question challenged orthodoxy. Each answer opened possibilities that conventional thinking had closed off. The result was an aircraft that didn't just match metal bombers, it outperformed them in key mission profiles while using entirely different resources. Second, the Mosquito showed how integrated design thinking creates advantages that component-level improvements cannot match. German designers were incrementally improving individual systems, more powerful engines, better superchargers, advanced armament. Each improvement made aircraft marginally better, but also more complex and resource-intensive. De Havilland took a holistic approach. He designed the entire aircraft system around speed as the primary survival mechanism. This single organizing principle drove every decision. No defensive guns meant less weight and drag. Less weight meant better performance from the same engines. Better performance meant higher survival rates. Higher survival rates meant smaller crews could accomplish missions. The cascading benefits of this integrated design philosophy created performance advantages that piecemeal improvements couldn't achieve. A German fighter might have a better supercharger or more advanced armament, but the Mosquito's entire system was optimized for a different objective that proved more valuable in practice. Third, the Mosquito validated the importance of matching production methods to available resources. This seems obvious in retrospect, but it was radical at the time. The prevailing assumption was that modern warfare required modern materials and methods. Wood was seen as obsolete not because it couldn't perform, but because it didn't fit contemporary definitions of advanced technology. De Havilland recognized that strategic value comes from what you can actually build and deploy, not from what's theoretically best in ideal circumstances. Britain could build Mosquitoes in large numbers using resources that didn't compete with other programs. Germany could build technologically superior aircraft in small numbers that couldn't affect strategic outcomes. The choice between building 200 adequate aircraft or 50 superior aircraft isn't always clear-cut, but the Mosquito demonstrated that adequate aircraft you actually have often beats superior aircraft you're still trying to build. Fourth, the Mosquito illustrated how psychological factors shape military effectiveness as much as physical capabilities. The aircraft's success wasn't just about speed and altitude. It was about what that performance meant psychologically for both sides. For British crews, flying Mosquitoes meant high survival rates and successful missions. This built confidence and morale. For German defenders, Mosquitoes represented frustration and impotence. They could detect them but couldn't stop them. This eroded confidence in equipment, tactics, and ultimately in the war's outcome. The propaganda value was enormous. Britain could demonstrate air superiority over Berlin itself, photographing the Reich capital in daylight while German fighters watched helplessly. The message was clear. British aircraft could go anywhere, anytime, and German defenses couldn't prevent it. Fifth, the Mosquito proved that operational flexibility has strategic value beyond any single mission type. The aircraft served effectively in reconnaissance, bombing, night fighting, ground attack, anti-shipping, and pathfinding roles. This versatility meant production could continue regardless of changing tactical requirements. It simplified logistics and training. It allowed commanders to repurpose aircraft as situations evolved. German specialized aircraft might perform better in specific roles, but they couldn't adapt to different missions without extensive modification. The Mosquito could shift from reconnaissance to bombing to night fighting with relatively minor changes. This flexibility had value that single mission optimization couldn't match. The human dimension of the Mosquito story deserves particular attention. Behind every technical decision were people making choices under enormous pressure. De Havilland persisted for years despite repeated rejection because he believed in his vision and understood Britain's strategic needs. Air Ministry officials eventually authorized the prototype despite skepticism because they were desperate enough to try unconventional approaches. Test pilots risked their lives proving the concept. Production workers adapted furniture-making skills to aircraft construction. Combat crews flew dangerous missions, trusting that speed would protect them better than guns. Each person in this chain contributed to success that no individual could have achieved alone. For German personnel who encountered the Mosquito, the experience was profoundly disillusioning. Fighter pilots who had trained extensively, who flew advanced aircraft, who had achieved victories against other opponents, found themselves unable to engage this wooden British machine effectively. The frustration in combat reports is palpable. Target maintained speed advantage throughout engagement, unable to close to firing range. These weren't failures of courage or skill. They were systemic limitations that individual excellence couldn't overcome. The Germans had committed to an approach that couldn't counter what Britain had created. Recognizing this required intellectual honesty that organizational culture often resists. The intelligence officers and engineers who examined the captured Mosquito faced similar challenges. Their analysis revealed uncomfortable truths about German technical assumptions and strategic choices. Reporting these truths accurately meant acknowledging that the enemy had done something genuinely clever, that British designers had found solutions German engineers had missed. In an authoritarian system that emphasized national superiority and punished bearers of bad news, honest assessment was professionally dangerous. Yet the assessment had to be honest, because lives and battles depended on understanding reality accurately. The Mosquito's post-war legacy extended into Cold War aviation development. The concept of speed as survival influenced designs like the English electric Canberra, which used jet propulsion to achieve similar operational philosophy. Fly fast and high enough that interception becomes difficult or impossible. The American U-2 and SR-71 reconnaissance aircraft took this principle to extremes, operating at altitudes and speeds that made interception nearly impossible with contemporary technology. These aircraft owed conceptual debts to the Mosquito's demonstration that reconnaissance aircraft could survive through performance, rather than defensive systems. The multi-role fighter concept that dominated late Cold War and modern aviation, aircraft like the F-4 Phantom, F-16 Fighting Falcon, and FA-18 Hornet, reflects lessons the Mosquito taught about operational flexibility's value. Building specialized aircraft for every mission is expensive and logistically complex. Building adaptable aircraft that perform well across multiple roles is often more strategically sound. Modern composite materials in aircraft construction echo the Mosquito's innovative use of laminated wood. Today's carbon fiber composites offer strength-to-weight ratios superior to metal, just as properly engineered wood did in the 1940s. The principle remains consistent: use materials that best serve performance objectives regardless of conventional preferences. The Mosquito proved this principle in the most demanding test environment imaginable: combat against a determined enemy with its own formidable capabilities. The Wooden Wonder succeeded where metal bombers struggled, demonstrating that unconventional approaches, when properly conceived and executed, can achieve results that conventional wisdom insists are impossible.